of our community, which is Pooja Ravi and Aditya Shukla. Starting with the session, we are having Pooja Ravi. So she would be having a walking through about the entire starting of the sequence models, and followed by him would be Aditya Shukla. So without wasting further much time, let's go away with it. So yeah, over to you, Pooja.
Okay, thank you, Harsh. So, hi guys, welcome to day 4 of NeuRes Deep Learning webinar. I'm Pooja, and with me I have Aditya Shukla, and today we're going to be talking about sequence models in great detail. So stay tuned and let's get started by looking at the topics that we're going to cover for today. Next slide. Okay, so firstly, we'll be talking about what sequential data is, because once we understand why sequential data is different from numerical data, we can move on and talk about some sequential models. So then we'll talk about RNNs, the intuition and working, and some drawbacks that they face. And because of these drawbacks, we'll also talk about some better alternatives like GRUs and LSTMs. Finally, we'll talk about some recent breakthroughs in the field of sequence modeling. So next slide. Okay, so here you can just see our faces. I am Pooja Ravi, a deep learning researcher, and I have with me Aditya Shukla, the Associate Technical Director of Data Science Community. So next slide. Okay. So now that the formalities are done, let's get started and talk about sequential data. Okay, so you see this sentence right here, highlighted in pink. It says, this sentence is a sequence of words. Obviously, we are able to understand what the sequence is conveying because these words are arranged in a certain order and they make the sentence grammatically and semantically correct. So let's say that we mixed up the words in the sentence, right? Let's say we had something like sentence this, sequence is, words of a. So obviously that made no sense to you or me, and it obviously won't make any sense to the model either. And because this order is very important when it comes to sequence models, they need to be able to preserve this order or maintain this order when they're getting trained on the data. Let's talk about that in a little while. Let's first look at some more examples for sequential data. So here we have an audio waveform. This is also sequential in nature because it's arranged according to time. And we also have time series data in which a quantity increases or decreases with respect to time. So next slide. So I hope you understood the importance of sequence when it comes to sequential data or order. So we are going to talk about sequence models here because they are loop mechanism. So I know many of you might have already been introduced to feedback mechanism or looping in other subjects, but here the context is a little different and we'll see how. So let me just tell you, let me just summarize what this feedback looping mechanism is. Basically, take a part of the output from the previous time step and combine it with the current input from the current time step. So right now that might seem a little vague to you, but as we move ahead and look at some diagrams, it will become extremely clear. So for now, you just need to know that they take a part of the output and combine it with the current input. This is the mechanism for sequence models. So now let's talk about why we need a separate architecture. Like why aren't the pre-existing models enough to deal with sequential data? So let's take CNNs or convolutional neural networks. So they are really good when it comes to focusing on the regional aspect of data. That is pixel values, passing filters through images and so on. You just had a CNN lesson a few days ago. So obviously they can do this, but they give no importance to something called the temporal aspect of data or the sequence that we talked about in the first slide. And even when you take multi-layer perceptrons or simple artificial neural networks into consideration, they are also really adept at working with numerical data. But when it comes to focusing on the order that the data is being fed into, then you'll have to add some kind of different mechanism or a unique mechanism to deal with this order. So let's move on to the next slide. Okay, so before we dive into RNNs, let's just see what sequence models can build. So first up is sentiment analysis. Here, what's happening is tweets, texts, or reviews are classified into 3 different categories. For our example, we've taken 3. That is positive, neutral, negative, and there can even be some more classes. That is basically sentiment analysis, and sequence models are used for this task. Then we've got speech recognition. This I feel like many of us would have used in our day-to-day lives. This is basically when the model recognizes a human's voice and tries to make sense out of what the human is saying. So this is employed in Google Home or Amazon Alexa and so on. So then we've got text summarization. Here, what happens is when the user feeds in a long document or a long paragraph, the model will be able to generate a concise or a very precise summary of the same. Then we've got time series forecasting. Here, what happens is the quantity that changes with respect to time is fed into the model, that is the past data, and the model is supposed to predict the same for the future. Then we've got two slightly advanced applications of the same, which is music generation. First up is music generation. So here what happens is when a sequence of notes are fed into the model is supposed to predict a newer sequence of notes that will make a good fit as the successor to the input. That is, that is the best I can do to summarize what music generation is. It has a lot of theory behind it, so I hope you guys can go and explore it later on. Next up is image captioning. That is yet another breakthrough in the field of sequence modeling, where you input an image and you are able to somehow generate a caption for the image based on what the model thinks is accurate for the image. So we'll talk about this in the recent breakthrough section of this session. So let's move on. Next slide, please. Okay. So we've got recurrent neural networks, the first sequence model for the day. Okay. So next slide, please. Okay, so we've got an image here comparing recurrent neural networks to feed-forward neural networks. You can very clearly see that there are loops here that are not present in the feed-forward neural network. And these loops are the ones I talked about when I told you that there is a feedback loop mechanism. These loops do nothing but facilitate passing information through time. So I need you to really remember that and drill that point into your mind. They pass information through time. It does not mean that they're going to sit and loop over the same unit again and again. That's not what it means. They simply facilitate passing information through time. I hope that's clear. Let's move on to the next slide. Okay, so we've got the hidden state. So this solely facilitates that passing information through time that I talked about. The hidden state it's nothing tangible, it's nothing physical. It is a mathematical function which basically takes in a part of the output from the previous time step and combines it with the input of the current time step. I already told you this when I introduced sequence models. So here it says that it's put through a nonlinear activation function. What is this nonlinear activation function? In our case, it is tanh, which basically squishes the input values into a range between -1 to 1. Why? Because the model can make computations more efficiently and quickly. So for now, I've explained hidden state verbally. Let's move on and look at the mathematical functions I was talking about. Next slide. One second, let me just have some water.
Sure.
Okay. Okay, so here we start to decode the feed-forward mechanism in RNNs. So we've got three very important weight matrices. So we've got WXH, which is the input weight matrix. We've then got WHH, which is the hidden state weight matrix. And we've got WYH, which is the output weight matrix. So why are they important? Like, why do I need to remember this? So you know that the weight matrices are what get updated in any neural network, right? They are what help us minimize the loss function. So hence, what makes these weight matrices special, that is RNN special, is the fact that they are shared throughout time. So this is another point that you need to remember. They are shared throughout time, as in through each and every unit. We have an image in the next slide, so I'll explain it clearly. But you just need to remember that they are shared throughout time. Okay, so now we have a mathematical function coming up, warning. So this is the function for hidden state, which is nothing but what I mentioned in the last slide. See here, you have tanh and you've got the current input x of t. You've also got h of t minus 1. So they are multiplied by the respective weight matrices, that is WXH and WHH. Okay. So a combination of them, as I suggested, is what is being passed into the tan H activation function. And why do we use tan H? Because we want to switch them between -1 to 1. Okay, I hope that's clear. If you want, you can just like stay on the slide for a second. I need some more water. Okay, so I'll just like explain this again. So current input multiplied by the input weight matrix combined with or added to the previous hidden state, the previous time step's hidden state multiplied with the hidden state weight matrix passed through a nonlinear activation function tan H. Okay, so next slide. Here we have a diagram. I can, really drive my point here. Okay, so before that, I'll just tell you how loss is calculated. So first up is y hat naught, or the one you see here, right? Y hat naught. That is the model's prediction for that time step. Okay, so y hat naught is basically the hidden state passed through another activation function. That's it. Y hat naught is basically the hidden state passed through another activation function. And when this prediction is compared to, when this prediction is compared to the ground truth, the value that already exists, the value that the model is supposed to match, or the ground truth, this becomes our loss. Okay, when y hat naught is compared to y, our loss value is obtained. And all the loss values, L0, L1, L2, so on till LT, are then summed up to get the final loss, which is nothing but L. Okay, minimizing this loss is our end goal. It is the end goal for any neural network because the model is supposed to match real-time performance, right? So minimizing this loss is extremely important. So, okay, let's take the cell here, the first cell, okay, x naught, y hat naught, and so on. First, you have your x naught, which is the current input that I was talking about. Then you have wxh, which is the input weight matrix. This green box, don't be intimidated by it. It is just where the calculations for hidden state happen, right? Once that is done, you calculate your output by multiplying that with the output weight matrix and passing it through an activation function. And finally, you get your loss. So I hope the feed-forward mechanism is clear. And this hidden state, as you can see, those tiny little arrows, it's passed through each and every time step consecutively. So I hope that the feed-forward mechanism is somewhat clear, if not fully. Anyway, let's move on to how loss is minimized. Okay, we all know what backpropagation is. How you update your weights in the neural network in order to make training faster and more accurate, right? But here we just make a slight modification to get backpropagation through time. So what is it? How is it different? Why are there two extra words? Okay, let's look into that, right? So backpropagation through time basically sends all the gradients that you calculate back through the neural network and across each and every time step simultaneously. So that is what happens. And when you're updating your weight matrices, you update them uniformly throughout time. So that is a very important fact here, the fact that you update them uniformly throughout time. So this does not happen in CNNs or artificial neural networks, simple artificial neural networks. So what is calculated here? There is a lot of math involved in BPTT or backpropagation through time. So basically, loss is a derivative of the loss is taken with respect to each of the three weight matrices. I think that if we go to the next slide, you will be able to comprehend all this better. So let's just move on to the next slide. Okay. So here I have an image. So you know the feed-forward mechanism. It's represented in the with black arrows. When you come back, that is, when you backpropagate, you calculate the derivative of loss L naught with respect to y hat naught first. Let's say you want to update your output weight matrix, right? So first you take the derivative with respect to y hat naught, and then you take the derivative with respect to the hidden state multiplied by the specific weight matrix, and then you finally take the derivative of the hidden of the weight matrix you take the derivative of the product that you have with respect to the output weight matrix. So let me just repeat. I think I got a little confused there. So you have your L naught. You take your derivative with respect to the predicted value or y hat naught, that with respect to the hidden matrix, and the hidden matrix with respect to the output weight matrix. So then you get the delta value that you're supposed to update your weight matrix with. So I hope that's clear. You can just like look at this diagram for a while and try to comprehend what's going on. This is what happens in each and every time step, right? So when you back propagate through time, I told you you send all your values back through each and every time step, also across each and every time step. The red arrows represent the back propagation pass. So you can take a while to ponder over whatever I've just explained right now and collect yourself, calm yourself down, and you can have a break for a few minutes, and then Aditya Shukla will continue and talk about and will explain some code, some Python code representing RNNs. Okay.
We'll just take a few 5 minutes break because I know there's a lot of theory to just bombard you with. So take a couple of minutes and try to absorb these ideas. So we'll see you in 5 minutes. All right, guys, I think we can start again.
Yep, let's begin.
All right. So I'll take over now. Okay. So what have we talked about till now? We've talked about RNNs, and we wanted to show you the structure or the skeleton of what the RNN cell looks like. And so this is not the entire code, because there's a lot of code that goes behind even a simple RNN cell, from the parameter updates, and there are a lot of complicated equations. But I wanted to give you an idea of what the structure of an RNN cell looks like. How do the concepts that we've seen so far translate into programming language? So what we have here is a Pythonic implementation of an RNN cell. We have two functions in it, one to initialize the parameters and the values, and one to actually do the calculations. So here you'll see the three weight matrices that Pooja was talking about. First, we've got WXH, we've got WHH, and WHY. The first weight matrix, WXH, maps the current cell input X to the hidden state H. So you can think of the notation like that. The second one maps the previous hidden state to the new hidden state that we're going to calculate from the current recurrent cell. And the third one maps the hidden state that we've just calculated to the output, WHY. So we randomly initialize these weight matrices with the proper dimensions. So you don't need to bother yourself much with this stuff. And now coming to the hidden state. So if I just go back to this diagram, you can see that each recurrent cell is getting a hidden state from its previous recurrent cell. But for the first one, it doesn't have any previous hidden state because it's the first time step. So we need to initialize our hidden state to a vector of zeros. And that's exactly what we do. Now, there's some debate as to whether you should initialize it to zeros or to random values, but researchers have found that it works best when you initialize your hidden state to a vector of zeros. So now that we've initialized all the parameters, now we can actually do all the calculations. Now, these two lines may seem a bit daunting to you, but they're really not. They're very simple, and Pooja talked about them. So here we're taking the current cell input X, as you can see, and we're multiplying it by its weight matrix WXH. Then we're taking the previous hidden state H, multiplying it by its weight matrix WHH, adding the two, putting it through a tan H, and we've got our new hidden state. It's the same formula that Pooja talked about. Once we've got our new hidden state, then we'll just multiply that by the weight matrix which maps H to Y, which is WHY, and from that we've got our prediction, which is Y hat. That's basically it. And there are a lot of more lines of code that go beyond that go behind the back propagation through time stuff, but we don't need to bother ourselves with that. We have Keras and PyTorch libraries which take care of all that stuff for us. But I wanted to show you the skeleton of the code. All right. Excuse me. All right. So what is the problem with RNNs? As you'll find, in most industry implementations, RNNs are not the sequence points that are being used. We usually use some variation of the GRU or the LSTM, which we'll talk about, or something called the bidirectional LSTM, but we rarely, if ever, see recurrent neural networks in their simplest form being used. Why is that? What is the disadvantage that comes with the recurrent neural networks? As we have seen so far, the essence of the RNN was to be able to store memory, that is information about the past that can inform future decisions. But the problem with RNNs is that of vanishing gradients. Now, I'd like you to pay attention to this point. To summarize this as simply as I can, when we backpropagate through time, our gradients tend to become smaller and smaller very rapidly, and this is something that happens. Now, how exactly? If I just jump back to this diagram, as Pooja explained, we take the final loss, and with respect to it, we calculate our derivative or our gradient values. But since you can see we're calculating, since we're using the chain rule, we're going to have to differentiate once, then twice, then thrice, and then here, and through this side. And so you can see how many computations there are, right? And since this is just for one time, so if we're training for multiple epochs, then it's going to keep happening and happening. So because of so many computations, there is a very great chance that our gradients decrease very rapidly, almost exponentially. And gradients are the values which we use to update our parameters, right? If the gradients are too small, then parameter updates are going to be very slow, right? So let me try to use this equation to drive this point home. This is not the exact parameter update equation which is used in recurrent neural networks, but it'll help elucidate the idea that I'm talking about. Our new parameter is found by taking our old parameter and subtracting from it the gradient times the learning rate. Now, if the value for the gradient is too small, then we're hardly going to be subtracting anything from our parameter. and our parameter updates are going to be very small, infinitesimal in fact, and hence learning is slowed down. A machine learning model is going to have a really hard time learning any useful information. And what this means is that the further back we look in time, the less and less information from then is being remembered, meaning that older information is not given as much importance as newer information. Let me repeat that because it's important that you understand that. The further back we look in time, the further back we backpropagate, you can think of it like that. The further back we look, the less and less information from then is being remembered, and that means that older information is not given as much importance as newer information. All right. This is a big problem, but why? Why is it why is it important for us to be able to remember things from way back in a sequence? Have a look at the following sentence. The cats which already ate all their food were full. Now, if I were to try to build a recurrent neural network and I gave it the task of, given this sentence, barring this word right here, the 9th word, say I gave it a fill in the blank task, and I said, given this entire sentence, barring this word, what word should come in this blank? Tell me. Now, if I were to give this task to you, or to any human being for that matter, it's pretty simple. The cats which already ate all their food, dash full, probably were full. Now, if I were to tweak this a little bit, if I instead said the cat which already ate all its food, dash full, and then I asked you to do the same operation, then you'd probably say was. So how did you change your answer in that scenario? I think it's pretty self-explanatory. This thing right here, the subject of the sentence. The subject of the sentence is plural in this case, so we know that were is the tense that should come here. On the other hand, if this was cat, then the word here would be was. So what this means is that in this scenario, the 9th word was impacted by the 2nd word in the sentence or the 2nd word in the sequence. And if an RNN was given this task to fill in this blank, then it would probably not give you the correct answer because it can't remember information from all the way back in the sentence, the 2nd word. And that is the problem of long-range dependencies. These long-range dependencies need to be remembered so that they can help inform future decisions. All right. And this precisely is where GRUs and LSTMs come into play. GRUs are adept at handling long-range dependencies, and with the GRU, we begin to emphasize this idea of holding on to memory over a long period of time. All right. So just give me a minute. Okay, so let's talk about the gated recurrent unit, or the GRUs. GRUs, as the name suggests, introduce the concept of a gate in a recurrent unit. And we also introduce the idea of the memory cell, which we've seen as the hidden state so far, whose job it is to hold on to useful data, which may come in handy in the future. The novel idea here is this. At each time step, the respective recurrent unit generates a new candidate for the memory cell and offers it to the update gate. It can be thought of as that unit offering some insight from its particular input that can be stored in the memory cell to potentially be used later on. So let's see this in action. If we go back to our cat sentence, the cats which already ate all their food were full. If I were to feed the sentence to a sequence model, I would feed it one word at a time. The would go as the first recurrent cell, cats would go into the second recurrent cell, which would go into the third recurrent cell, fourth, fifth, sixth, and so on. So here each word will be fed to a recurrent cell. The second cell, cats, will offer some insight from its own input, right, which is the word cats, and it will offer this insight to be stored in the memory cell, right? And let's say our model, which is trained and now very smart, shall store this insight in the memory cell because it knows that this word is useful against the subject of the sentence and it will probably help inform a decision in the future. Now, as we traverse through the rest of the words, which already ate all their food, each of those words are going to offer us some candidate from their own word. So which will offer us some insight from the word which, already will offer some insight from already, ate from ate, and so on. But our model knows that these words don't really offer any useful insight. And the useful insight was offered by the word cats, the subject of the sentence. And so it holds on to that memory. It doesn't let go of that memory. And so each of these candidates offered by all these intermediate words will be declined by our model. And so the update gate, it declines this offer each time. And finally, our memory in the form of the word cats comes in handy when we correctly predict dash, so were full. All right, I hope you understood that. Now, I'm really sorry, but here is the mind-boggling part of machine learning again, mathematics. I try to avoid it, but I don't want to because it's important that you understand this. And these equations are really not as complicated as they seem. All these Greek symbols have a way of sort of, complexifying very simple ideas, but I'll walk you through it. So on the top right here, you see the diagram of a gated recurrent unit, and there's a lot of stuff happening here. So let me just break it down for you bit by bit. Xt is nothing but the current input, right? So like I told you, each cell will be fed one word. So xt is that one word, xt is that input. ht minus 1 is the hidden state from the previous cells, right? So it's the memory that we've retained so far. ht is the hidden state that we're going to be sending to the next recurrent cell. This bit right here, the zt thing that you see, that's our update gate. I'm going to talk about that. This bit is our reset gate. Now, I've not talked about the reset gate till now, but I'll shed light on that as well. This is the reset gate. This is the update gate. This h tilde t, this h with the squiggly line on top of it, that's called a tilde. So that's an h tilde t. H tilde t is our new candidate, the candidate that is offered by our recurrent cell, which includes some insight from the current input. So let's break this down. We take the current cell input xt and the previous hidden state ht minus 1, and this operation right here where the two lines are intersecting, it's nothing but a concatenation, and it's represented by this bracket right here in these equations. This bracket represents a concatenation. So we're taking the current input xt, we're taking the hidden state, and we're concatenating those two values. Then we're multiplying it by a weight matrix wz, as you can see right here, and we're putting it through a sigmoid function. The sigma that you can see right here, that's a sigmoid function. And from that, we get the value zt, which is our first value. Now, zt is our update gate. Zt is the value between 0 and 1. The purpose of the sigmoid is to squish the output between 0 and 1. So you can think of it like a percentage. The update gate tells us how much of the current input is useful information and should be stored in the memory cell to potentially be of use to us later on. So zt tells us how much of the current input is useful, right? So you can think of zt as a percentage. So if the value for zt was, say, 0.87, then that would mean that 87% of the current input is useful and it should be stored in the memory cell. That's what zt tells us. And very, very similar to this is the reset gate RT. We again take the same two values, ht minus 1, xt, concatenate the two, this time multiply it by a separate weight matrix, wr, and then we pass through a sigmoid. Once again, the sigmoid gives us a value between 0 and 1, and that value tells us how much of the memory that we've held on to so far, how much of the hidden state should be retained and remembered, and how much should be discarded or done away with. So it's sort of like a trash mechanism where we remove the useless stuff and only retain the important stuff. That is the purpose of the reset gate, and that's the value RT. This will also be between 0 and 1. From the value of RT, now we can generate our new candidate h tilde t. So it's once again a very similar calculation. We take our current input xt, but this time we don't take the entire hidden state ht minus 1. We only take RT part of it. And because RT was a value between 0 and 1, once again, you can think of this as a percentage. So we're only taking RT percentage of ht minus 1. Once we've gotten these two values concatenated, we're going to multiply this time once again by a separate weight matrix, W, and we're going to pass it through a tan H nonlinear activation function. From that, we're going to get our candidate. And once again, tan H just squishes the values between -1 and 1 so that they're easy to work with. All right, so that's a lot of information, but let's put it together. Let's put all these pieces together now. We've got a new candidate, h tilde t. We multiply h tilde t with the value of our update gate. And recall, the update gate tells us how much of the current input is useful and should be remembered. So we multiply that value with our candidate. We multiply the complement of that value with our previous hidden state. So let's say hypothetically that the value of zt was 0.92. Right? What that means is that 92% of the new candidate ought to be remembered and stored in the memory cell, and 8%, I said 92, right? So 8% of the previous hidden state should be remembered. So that's exactly what we're doing. I think it's pretty straightforward, and because the values are between 0 and 1, it's easy to relate them to percentages. So I hope you got that. And I'll just stay on this slide for half a minute about, so that you can sort of build the pieces up in your head and put it together. All right, guys, I hope you understood the gated recurrent unit. Let's move on now. Now, this is just the same thing, but written down in text. So I'll go through it one last time because I want you to understand this. We concatenate the memory state from the previous cell, ht minus 1, and the input into the current cell, xt. Their product is matrix multiplied by WR, and we sigmoid it, and this decides how much of the old memory state should be retained as useful information. This is the reset gate. And we do the similar thing for the update gate. This time it's a separate weight matrix, and this tells us how much of the new candidate offered will be taken as the new memory state. And this is just the same stuff that I've been telling you, but you really only need to read the last line here. What we've effectively done is take ZT percentage of the new candidate and 1 minus ZT percentage of the old memory state or the hidden state. That's it. So now I think we can jump on to LSTMs, or long short-term memory networks, where we really begin to emphasize this idea of the long-range dependency. All right, cool. So in LSTMs, we have a total of 3 gates: forget gate, the input gate, and the output gate. Before I jump on to explaining the purpose of each of those gates, let me talk about a new quantity here, the cell state. Now, you've heard the words before in this. You've heard these words before in this presentation, but in LSTMs, it's a little bit different. In LSTMs, we have a value called the cell state in addition to the hidden state. Now, it's important to distinguish between the cell state and the hidden state, because the hidden state is present in RNNs as well, but the cell state is an addition of the LSTM model. The cell state stores the long-term information about a sequence. That is, it's the primary long-term memory element of the network, whereas hidden state stores only the short-term working memory, right? So I hope you got that. Cell state, long-term, hidden state, short-term. That's about it. So now we can jump on to the forget gate and the input gate. Now the forget gate is very, very similar to the reset gate of the GRU. We take the previous hidden state ht minus 1, the current input xt, we multiply it by a weight matrix, pass it to a sigmoid. It's pretty much the same thing. And recall that the closer the values output by the gate are to 0, the more we're going to forget or discard, and the closer that they are to 1, the more we're going to remember. All right. So let me just show you the GIF, which will really help drive this point home. So we're taking these two values, concatenating them, putting it through a sigmoid function, and that's it. And once we've got this value for the forget gate, once again, recall that the sigmoid tells us gives us a value between 0 and 1. So we multiply this value by the cell state from the previous cell, ct minus 1. And from that, what we're doing is we're taking the cell state and we're retaining only the useful information from that. And how much useful information should we retain? That's decided by this guy right here, the forget gate. Okay, let's talk about the input gate. The input gate decides which data from the current cell input is to be stored in our cell state. And like you can probably spot, it's pretty much like the update gate of the GRU. So we take the previous hidden state, the current input, concatenate them, weight matrix obviously, and pass them once to a sigmoid and once to a tan H. Now what is this? Like, why am I passing it to two separate things? Let me try to elucidate that. Just watch this GIF for a second. It's pretty clever what's happening here. So I'll try to elucidate this. We're taking the same concatenated values of those two, and we're passing it to two separate functions now. One function is a sigmoid, right? We're passing it to a sigmoid, and that is returning a value between 0 and 1. And the other time, we're passing it to a tan H, and that returns us the value between -1 and 1. So basically what we're doing is the sigmoid returns a value which tells us how much of the current input is useful, and tan H is just the input but squished between -1 and 1. So when we multiply these two values, all we're doing is taking this output percentage of this thing. I know it's a bit abstract, but I'll try to explain this once again. The sigmoid tells us how much of the current cell input is useful, and this is just the same data but switched between -1 and 1. And when you multiply these two, we're just taking the useful percentage of our current cell input to be stored in the memory cell. So I think that was pretty clear. All right, so once we've got these two values multiplied, and this is, by the way, an element-wise multiplication. This is not a matrix multiplication. We're just multiplying these two values element-wise. And I think that'll be pretty obvious since it's the same value being put through different activation functions. Okay, so now that we've got that down, we can talk about the output rate. But before that, we need to talk about the next cell state. So as you can see in this in this diagram, the cell state coming from here, from the previous cell, also after all this calculation needs to be routed to the next cell, right? Because it's a long-term memory element. So once we've gotten the value, this value right here, and once from the forget gate, we have taken only the useful part of our cell state, we add these two values, and then we send that value right on to the next cell. So just to repeat that and drive that point home, we take the output of the input gate, we take the output from the forget gate, and we just add the two element-wise, just an element-wise simple addition, and we pass it on to the next cell. That's it. Okay, now the output gate. Finally, we have the output gate. Here we take the current cell input, the previous hidden state, put it through a sigmoid, and we also take the cell state which we just calculated and multiply the two. All right, so let's see that in action. This is the output gate, right? It's the same value, put it through a sigmoid, take this value, element-wise multiplication, and we've got our new hidden state HD. So you can see it's just the same calculation but in different flavors, right? We're taking the pretty much the same value for the forget gate, for the input gate, for the output gate. You know, it's just a slightly modified versions in each part. So finally, for the output gate, just to recap, we're taking this value that we just calculated, we're taking the sigmoid of this value, element-wise multiplication, that's our new hidden state, passing it on to the next cell, and that's pretty much it. So I think that's pretty much it from my side, and I would like to hand it over back to Pooja so she can go ahead. Pooja?
Okay, so now I'd like to show you some Python code that will basically represent what an LSTM cell looks like, and it has been coded using NumPy library in Python. So let's first go to the next slide and see the code. Okay, so we have a function here. This basically has three different parts: the forget gate, input gate, and the output gate, as explained by Aditya. So for a second, just take this in. Look at the notations that we have right here. So I've represented all the different variables that I've used in this little box here. So we've got W forget for forget gate weight matrix, input for xt is input, and so on and so forth. So let's first begin with the forget gate. So let's go back to the image. Okay. So the first portion is the forget gate. Aditya has already explained what happens here. The forget gate decides what part of the previous cell state needs to be retained. So how is that done? We basically pass the previous hidden state combined with the current input through a sigmoid activation function. So the sigmoid basically gives you a probability value between 0 and 1. If it's close to 0, you can just discard it without any second thought. And if it's closer to 1, you need to retain the same. So this value, this probability value, is then multiplied with the previous cell state. Okay, so let's see the code for the forget gate. So we've got, right here, we've got the combination, previous hidden state, and we've got the current input combined together, multiplied by the forget gate weight matrix. So let's not forget that. So then we pass the whole thing through a sigmoid activation function in order to get our probability value. Finally, it gets multiplied to the previous cell state, C prep. So I hope the forget gate, the code for forget gate is clear. Let's move on to the input gate. What is the functionality of this gate, right? So as Aditya already explained, the input gate basically decides what should be added to the pre-existing cell state. What part of the input needs to be added, okay? Let's go back to the image. Okay, so the second portion here that's being highlighted is the input gate. So we've got a combination of the previous hidden state and the current input being passed through a sigmoid yet again, because we need to get the probability value. And the tanh is to basically squish the value between -1 to 1. So when we multiply this probability value with the squished value, we basically get what we need to update our cell state.
Um,
Um,
and did I stop presenting?
what happened? Yeah. I think you
Sorry.
stopped presenting. Yeah, no problem.
Is it visible now?
It's loading. Yeah, okay. We're back. Sorry about that. So basically, this multiplication here tells us what is supposed to what we're supposed to retain from our current input, and the whole thing is added to our pre-existing cell state. Okay. So now let's look at the code for the same. Next slide. Okay, so here we've got the sigmoid. Okay, first let's look at this combination. The same thing, input and previous hidden state. But now you can notice that it's multiplied by the input weight matrix. So what makes these gates different is the fact that they multiply to their respective weight matrices. So I hope you understand what's happening here. And this whole thing is passed through the sigmoid function for the probability. Then we pass the same combination multiplied by the cell state weight matrix. You can see that there, and pass it through the tanh activation function. So when these both values, the in2 variable and the cell state calc, get multiplied, we basically get the part that needs to be added to the pre-existing cell state. Okay, see that's what's happening here. You have the current cell state, which is nothing but the memory part from the forget gate. Okay, the pre-existing cell state added along with the calculation that we have here, this multiplication. So I hope the working of the input gate is clear. So then we finally come to the output gate. This is basically used to calculate our current hidden state. So let's go back to the image. Okay, so here we've got the same old combination again, and we pass it through the same sigmoid function, y, to get the probability value. And here we're adding one more new thing, which is the cell state. The cell state is being, sorry, not adding, multiplying. The cell state is being multiplied with this combination now, because that is what determines, or that is what defines our current hidden state. Okay, I hope that's clear. Tanh, as usual, it is used to squish values between -1 to 1. So let's move on to the code. Okay, so here we've got the same thing. The combination input previous hidden state multiplied with the output weight matrix and passed through a sigmoid function, probability. Then we have np.tanh, which is nothing but the tanh using NumPy library. And finally, we get a hidden state by multiplying this variable, the output variable, along with our calculation. So that is pretty much it for the code walkthrough of an LSTM cell. Obviously, there's a lot more going on behind the scenes. And as Aditya said, you can find the same, it is already employed in a library like Keras. So you can find it there. So we've come to the final part of today's session. I'm really happy that we're here. So we have recent advancements or breakthroughs in sequence modeling. So after we finish discussing this, we can bid goodbye, right? So next slide, please. Okay, so we've got encoder-decoder models, or seq-to-seq. Okay, so what are they? Encoder-decoder models basically map an input with certain length to an output with probably a different length. The lengths of the input and the output need not be the same. Okay, so they have three very important concepts embedded into them. First up is the encoder, which receives the input and processes it, and basically compresses it and produces the intermediate vector or the context vector. This is nothing but a vectorized representation of the input that the encoder handles. Okay, this is then passed on to the decoder, and obviously the decoder works with this data in order to produce the model's output. So here you have an example of an encoder-decoder model. This is nothing but language translation, where English is being converted to German. So you can see here in the encoder, he loved to eat. Each and everything is being passed through a time step. And you can see that there is no output for each and every time step specifically, right? We don't get outputs from each and every time step. We get them only in the end in the form of S, or the context vector, or the. So I hope that makes sense to you. But one thing that the encoder decoder models also suffer from is the long term dependency problem. Right? They are not able to focus on data which is really long, or which has a lot of information stored in the beginning of the input. So because of that, we have yet another breakthrough that we'll explore. It will be the final one. Next slide, please. Okay, so we've got the attention mechanism. So, as I said, encoder decoder models, they basically put a lot of focus into the end part of the input data. So the context vector really pays a lot of what do you say? It pays a lot of importance to the end part of the data instead of actually paying attention to the relevant parts. And this is where the so-called attention mechanism comes in. It helps the encoder decoder models focus on what is relevant, what is necessary in the data, instead of actually focusing only on the end. So you can see here that it says pays attention while reading the input and stores these insights into the context vector. So I hope that has given some insight into what has been recently happening in the field of sequence modeling, and I really enjoyed giving this presentation. We've come to the end of the presentation. I'm very happy that I got to do it without the
Thank you, guys.
So,
Thank you really very much for giving us your precious time. We really appreciate it. And it's been an honor to present this presentation alongside Pooja. And this was proudly presented by Data Science Community at SRM. After this, we'll be having a quiz for you guys. So the link for that, as usual, will be shared on the NeuRes channel on our Outer Circle Discord server. So you'll see that link soon, and we'll share more details about that in a few minutes to come.
okay.
So yeah, hi guys. So first of all, very much thanks to Aditya Shukla and Pooja Ravi for giving a very good presentation. So it was a really good thing to have today. Like we had our day 4 for the NeuRes. We have just 2 more days to go for this session to end. Also, if you guys have any sort of queries or questions, please feel free to put them in the chat box, or you can even ask us in our outer circle of the Discord server. We would be
Right.
really glad to help you all. And also within a few minutes, we will be just posting out the quizzes link. So just
Right.
stay tuned for that as well.
Guys, we'll be sharing the link for the quiz. The link has already been shared, in fact, in our on our Discord server, and we'll be activating the form at exactly 6:30 p.m. and it will be live for 6:35 p.m. So try as fast as you can and get those responses in from the stuff that we've taught you. And all the best to you guys. All right, guys, the form is active, so you have 5 minutes. So all the all right, guys, that's it for today. Thank you for joining us, and we'll see you tomorrow